Welcome to Quantum Curious, and in today's video, we are going to discuss another property related to entanglement. So, in the previous video, we studied and saw what is entanglement and what are its properties and how is it different from classical correlation. So, in today's video, I'm going to discuss the purification of the reduced states. So usually we have the knowledge of the reduced state, but we want to build the larger system from which it is coming. So this is the operation that is related to purification of the state. So let's start with some kind of motivation. So we know that partial trace operation, and we could calculate easily the reduced state if we know the pure state or the larger state. So here we have a pure state and we want to calculate the reduced state of that larger system. We can calculate by applying the partial trace system on the system. We do not want to know, and we can uh, calculate the remaining system, that is the smaller system. And it is a reduced state we will get. So it is also the signature of entanglement. And if we know the whole state, and that is the pure state, and the state we are getting after the partial trace operation, and that is the state of a smaller system, and if it is a and if it is a mixed state, then it is a signature of entanglement. So how is it a signature of entanglement? We can see by this example. So we have a larger state and it is a pure product state, and if we take the partial trace operation on B of the density matrix of that pure state, we can see that the resulting density matrix is a pure density matrix and it corresponds to the pure state. So this is not the mixed state, and we could see that our previous assumption on the larger state is that it is a product state and it is not an entangled state. So if we have an entangled state, then we are going to have a mixed state in the form of the reduced state. So it is a very strong signature of entanglement if we get a reduced state that is a mixed state. So we have seen that how partial or trace operation works and how we can calculate the reduced state from this operation. So we want to know that is there a reverse of this operation present? In other words, can we calculate the larger state or pure state of the system by only having the knowledge of the reduced state? So the answer is yes, and the answer can be uh, is the answer is can be in the form of the purification. So purification of us to reduce state rho A is a pure state psi AB, and uh, we have a condition on the purification that the trace of B will give us back the reduced state rho A. So we will see that how we can calculate the uh, purification of any reduced state and what kind of properties it would have. So consider we have purification of rho A, and it is given in the spectral decomposition, and we know that we have state. So there is a typo error because it should have the outer product form. So we have the knowledge that uh, state, that is the reduced state rho A, is in state rho J or phi J with a probability distribution lambda J. So phi J here are orthonormal bases and lambda J is an eigenvalue, and we have the uncertainty in the system subsystem A, and This uncertainty would be a classical uncertainty or a quantum uncertainty. So classical uncertainty is that we have a machine and it is reproducing some state with some probability, and our ignorance is given the in the form of the density matrix. And there is a quantum uncertainty if the state is it entangled with another system, say B, then there is inherent randomness, and the system A is not in a definite state before the measurement. So let's see how this quantum uncertainty and how can we build the purification of that state by introducing another system B. So the question is that who controls which part of the mixture A is in? So in other words, we want to know that what kind of system controls s- the state rho A and uh, the condition on which it is being in the state phi j with some probability lambda j. So we can build another state rho AB, and that is the larger state. And here we have phi j, that is the reduced, that is the orthonormal states of subsystem A. And we have some orthonormal state of B, and it is in the form of the standard basis. And the whole state is the the pure state, and that is why it is called the purification of the reduced state. So if we take the density matrix, or if we calculate the density matrix of the whole state and take trace over P, we get back the reduced state uh, were were started with initially. So we could say that the psi state, that is the larger state, is a purification of reduced state rho A, and it could be built by any orthonormal basis with of system P. So there's a condition that it should be the whole state should be the pure state. So this is the idea behind the purification, and we could see that it is just kind of an opposite operation of the partial trace. So another question is that are purifications unique? In other words, can we build the purification of state row A by introducing another basis other than the standard basis? So the answer is yes, and uh, we have the unitary degree of freedom, because the eigen states, or the orthonormal states of state B, should be unitarily correlated with each other. So as long as they are unitarily correlated with each other, we can build the purification of state rho A by using any of the bases that are unitarily related with each other. So purification is not unique, and it is not unique as long as we have unitarily correlated uh, or unitarily related eigenbases. So, so we have seen that how the purification can be built, and the condition on the eigenbasis of the second system B is that they should be correlated or unitarily correlated with each other. So This question could also be answered by the Schmidt decomposition. So we have seen that kind of pure state, that is the product state. And how can we prove that we could build the purification or the Schmidt, or sorry, we should use here Schmidt decomposition, how we could build the Schmidt decomposition of the pure state or any entangled or any pure state. So we could see that here is one of the form of the Schmidt decomposition, and it is a general form of Schmidt decomposition, and where we have phi j and j, and they are usually called Schmidt factors, and square root of lambda j is called uh, the Schmidt rank or Schmidt coefficients. So uh, you can say they describe different properties of the state, and entanglement is one of the one. So we have a general state psi AB, and here we have some uh, vectors IA related to system A and vectors J with some relation with system B. And here are expansion coefficient of that state. So we start with that matrix of expansion coefficients, and we can build the single valued decomposition of that matrix where UK and BK are eigenvectors and alpha k are some kind of eigenvalues of that matrix. So we want to know the specific element of that matrix C. So we will get that element of matrix C, that is the Cij, by sandwiching in between state I and state J, and we get this. So here should be alpha k, and if you put that form in our uh, previous state, psi AB, we got this form. And we could see that we could build the state with eigenvalues alpha k and eigenvectors uk and bk related to the system A and B. So this is the Schmidt decomposition, and it has very important properties, uh, as we could quantify the entanglement of the state by this. So there are some consequences related to the Schmidt decomposition. So by knowing the Schmidt decomposition, we can compute the reduced state, and it is one of the important, you can say, advantages of the Schmidt decomposition, because if we do not know the form of the pure state, or if we do not know the specific form of the larger state in a simplified form, we cannot calculate the reduced states. So this is one of the advantage of the calculating the Schmidt decomposition of the state. And another consequence is that the state rho A and rho B, that are the reduced states of the system A and B, that is the larger system. The both system have same eigenvalues, or we could say both reduced matrices have the same eigenvalues. And this makes the whole idea of, you can say, information calculation very easily. Like if you want to know the entropy of system rho B, but we only know the specific form or the eigenvalues of the subsystem rho A. So we could invoke the Schmidt decomposition, and we could say that if both are part uh, of the same larger system, so they should have the same eigenvalues, and the entropy of both states should be same. So this is one of the advantages, and the Schmidt coefficients are just the square root of the eigenvalues of the reduced states. And there is the unique Schmidt factors. So if we have only one Schmidt coefficients, and so we are working in eigenbasis with uh, only one eigenvector. So in this case, the Schmidt vectors would be unique. On the other hand, if we have a Schmidt coefficient more than one and they are degenerate, like they have different eigenvectors, then we could have Schmidt vectors more than two or three Schmidt vectors. Then the Schmidt vectors would not be unique Schmidt vectors because we can build eigen vectors from the space of the eigenbasis. So in this case, the Schmidt vectors would not be unique if we have coefficient that Schmidt coefficients that are uh, degenerate and have more eigenvectors. And the last consequence is one of the important consequences of the Schmidt decomposition. So Schmidt rank is the number of Schmidt coefficients. So if we have only one Schmidt coefficient, then we have product state. And if we have a rank greater than one, then we have entangled state. So we could take the example of the EPR state. So EPR state is one of the best example to represent the Schmidt decomposition. So in that case, we have two Schmidt factors or two Schmidt coefficients. Then the rank is two, and it is strictly greater than one. Then we could say that the EPR state is an entangled state. So we have seen multiple times that how can we show the of the quantum entanglement property of the EPR state. So we could see that how how easily we can categorize the entanglement of a given state if we know that Schmidt coefficient or Schmidt decomposition of that state. So this is the for today. So we saw that what is purification, and we saw that how we can uh, get insight about the properties of the quantum state through Schmidt decomposition. So this is for today. We will see that how we can use these kind of properties of the quantum state like purification, partial phase operation, and Schmidt decomposition in the study of quantum cryptography.